Okay, so this lesson is on correlation and causation. It's chapter 5, section E. And when we talk about correlation, there's a correlation that exists between two variables when higher values of one variable consistently go with higher values of another variable, or the opposite, when higher values of one variable consistently go with lower values of another variable. We have examples of these correlations, and it says that there is a correlation between the variables and the height and weight for people. Well, that makes sense, right? As somebody's height goes up, their weight also goes up. This is a correlation. There's also a correlation between the variables for demand for apples and the price of apples. That is, the demand tends to decrease as the price increases. So obviously, if you've got one apple in Walmart and that's it, and everybody wants that apple, well, Walmart wouldn't, but they could charge whatever they wanted to for that apple because it would be in very high demand. When it's the only one left, right? The price is going to go up. There is a correlation between practice time and skill among piano players. So if we look at skill and practice time, it should be that the more you practice, the better you are at playing the piano. Establishing a correlation between variables does not mean that a change in one variable causes a change in the other. We can draw a scatter plot from this. A scatter plot is a graph in which each point represents the value of two variables. So here we are talking about infant mortality per 1,000 births and literacy rate. We're trying to see if there's any kind of connection here. So we want to put literacy rate here. And this is in a percent. And we would put infant mortality per 1,000 births on the left side of the screen or on your y-axis. So if we're plotting these points, we would want to plot the point 33, 63. So I'm going to go down here. So 33 is going to be about right here. 63, we're going to have to make estimates on these. 96, 2. So 96, 2. 88, 54. Right around in here. 94, 14. 52, 43. 99, 3. 50, 52. 99, 3. We already plotted that one. 99, 95, 12. 95, 12. And 99, 5. So 99 and 5. It's going to be a little bit higher than the... Okay, so when I look at this, I kind of see that there might be some kind of relationship going on between these two. It looks like that as infant mortality rate is higher, it looks like we have a lower literacy rate. If we were to draw a line of best fit, and we'll talk about what that is a little bit more, we'd want to try to hit as many dots as possible, but basically go in the middle of the other one. So a line of best fit might be about right here. I could use this to make predictions. In other words, if I have a literacy rate of 40, so if I go for 40 and I go over, I'm estimating that my infant mortality rate would be about 52%. It looks like as the infant mortality rate goes up, the literacy rate goes down. This is a negative correlation. As one thing goes up, the other thing goes down. We could also say the opposite is true here. As the literacy rate goes up, the infant mortality rate goes down. Okay. So relationships between two data variables. They can have no correlation, which means there is apparently no relationship between the two variables. This graph is a good example of that. We can't tell if it's going up or down. There's just dots everywhere. Positive correlation, they can either both variables tend to increase or decrease together. So positive correlation, the line's going to go up from left to right. A negative correlation means that one variable increases while the other decreases. Okay, and we can also talk about the strength of the correlation, whether it's weak or strong, and that's really how close the points are to the lines. Okay, so this is a positive correlation. This is a positive correlation here. I could draw my line of best fit. Seemed like maybe right around here. Might have gotten it a little bit too low. It seems like there might be too many on the top. This point is way outside what would normally be there, so this is probably what we would call an outlier. But this has a positive correlation. The weight in carrots is driven by, the price in dollars is driven by what the weight in carrots is. This one right here must be one that is maybe has a great clarity. Costs more, but it doesn't weigh as much. That could also be something that drives the price up. So this is a positive correlation, and it's actually not real weak. There are a couple points that are off, and once again, those are probably diamonds that have really rare clarity. But that's a positive correlation. As the weight of the diamond goes up, so does the price. Okay, a scatter diagram shows the higher life expectancy generally goes with lower infant mortality. If we were to come along here and draw a line of best fit, it may be something a little bit like this, okay, which is a negative correlation. You can see that the line is going down. It's a pretty strong negative correlation. There are some places, Russia is kind of way far away from the line, but we've got a pretty strong negative correlation, which means that life expectancy goes down, infant mortality rates go up, or vice versa. As infant mortality rates go down, life expectancy goes up in that country. So what about these two? Okay, to me, this has, I could draw a line of best fit here. Maybe something's like this. Okay, so I think it would go down. So I think it has a negative correlation. And the dots are pretty close to the line, except for maybe these two. So it's a pretty strong correlation. They're not exactly perfectly on there, but they're not way spread apart. This one down here, the dot, I couldn't even tell whether to draw the line up or down. This is a no correlation. It's an example of one that has no correlation. Okay, this one definitely is a very strong negative correlation because the dots are like all there together. So strong negative correlation. Okay, so scatter plots show 2 weeks of data comparing the actual high temperature for the day with the temperature predicted by the same day forecast, and the 3-day forecast is on the right. So what do we know about this? We know, let's just pick a point. Let's say this one. Okay, so this point is at, it looks like around 43, and if I go straight over, we're around 39. So this is the same day forecast. They said it was going to be 43, but in all actuality, it ended up being 39. Okay, that's just one point. Let's pick another point over here. Let's pick this one. So this is whenever they're picking it 3 days in advance. So I'm going to say the 3-day forecast. So it looks like at the 3-day forecast, they said it was going to be somewhere around 45 degrees, that point. And in actuality, when we got to the day of, the temperature was really around 35. If I was going to draw a line of best fit for these, okay, I had this. I can still tell that it's like a positive correlation, but these red dots are a lot closer to the line. This is a lot stronger of a positive correlation than the blue dots. This is a much weaker positive correlation, simply because it makes sense, right? If you're predicting the forecast 3 days out, you're more likely to not be spot on. Okay, so what's some possible causes or explanations for this correlation? The correlation can be just a coincidence, okay? That's one thing that can happen. Both variables might be directly influenced by some common underlying cause. And then there might be what we're trying to find most of the time is that one of them actually causes the other one. So we looked at this infant death rate and life expectancy. We looked at that one earlier. And what can we gain from that? Okay, so do we think that the correlation may be just a coincidence? Well, I don't think so, right? I don't think that is just a coincidence. We talked about the fact that there was probably something that had to do with economics that when we dealt with this, that would have affected that. So both variables might be directly influenced by some common underlying cause. Yeah, we think that maybe socioeconomic status affects both infant mortality and a low life expectancy age. Okay, and then the last one was one of the correlated variables may actually be a cause of the other. Well, no, because infant death does not cause early life expectancy for you to die early. Okay, so just because an infant dies early doesn't mean that would cause somebody else to die early. And just because somebody dies early, that doesn't mean that an infant's going to die early. So those don't cause each other. This would be an example of something that has an underlying cause. So we actually are seeing something here, but this one has an underlying cause. And the underlying cause is probably due to healthcare in poor countries. Not getting proper health care is probably, if we looked at another factor that was influenced by health care, like how many people had diabetes or things like that, that would probably be higher in these countries as well, because there's an underlying health cause. So consider the following real correlation. The stock market tends to rise for the rest of the year when a team for the old pre-1970s NFL wins the Super Bowl and tends to fall otherwise. So, in other words, if I have somebody who wins the NFL, if I have somebody who already had a team on the NFL before 1970 and their team wins the Super Bowl, then the stock market is supposed to do good. If the team was established after 1970 and they win the Super Bowl, the stock market's supposed to do bad. Okay, and so in fact, they come along and they find out that this is called the Super Bowl indicator, has a real name, and it's been correct 40 out of 50 times. So should you therefore make a decision about whether to invest on the stock market based upon the NFL indicator? Okay, so is this thing just a coincidence? Is it number one, or do both variables, are they directly influenced by some common underlying cause? In other words, is there something out there that causes the stock market to go up that also causes pre-1970s formed NFL teams to win the Super Bowl? Probably not. Do one of them cause the other? So do we really think that the NFL pre-1970s NFL team caused the stock market to go up? No. So I would say do not let this influence your investments. This is just a coincidence. We can find no other proof for this. It's just a coincidence. So when you're trying to establish causality, if you suspect that a particular variable is causing some effect, you want to look for situations in which the effect is correlated with the suspected cause, even while other factors vary. Number two, you want to, among groups that differ only in the presence or absence of the suspected cause, check that the effect is similarly present or absent. You can also look for evidence that larger amounts of the suspected cause produce larger amounts of the effect. Number four, if the effect might be produced by other potential causes besides the suspected cause, make sure that the effect still remains after accounting for those other potential causes. And if possible, test the suspected cause with an experiment. If the experiment cannot be performed with humans for ethical reasons, consider doing the experiment with animals, cell cultures, or computer models. Try to determine the physical mechanism by which the suspected cause produces the effect. So by the 1990s, we've got passenger side airbags had become commonplace in cars. Okay, and the statistical studies show that the airbag saved many lives in moderate to high-speed collisions. But a disturbing pattern also appeared. In at least some cases, young children, especially infants and toddlers in the child's car seats, were killed by airbags in low-speed collisions. Use the guidelines to determine possible causes. Well, at first, many safety advocates found it difficult to believe that airbags could be the cause of the deaths. But the observational evidence became stronger, meeting the first four guidelines for establishing causality. For example, the greater risk of infants in child car seats fit Guideline 3, because it indicated that being closer to the airbags increased the risk of the death. A child car seat sits on top of the built-in seat, thereby putting a child closer to the airbag than the child would be otherwise. To seal the case, safety experts undertook experiments using dummies. They found that children, because of their small size, often sit where they could be easily hurt by the explosive opening of an airbag. The experiments also showed that an airbag could impact a child's seat hard enough to cause death, thereby revealing the physical mechanism by which the deaths occurred. So what they found is we have this underlying cause. The child seat sits too close to the airbag. We have this underlying cause. Which is causing them to have more deaths. So they did further testing to reveal that. Okay. The issue of cell phones and driving has followed a trajectory similar to that of airbags in children. The correlation between cell phone use and car crashes was also thought to be coincidental at first, because talking on a cell phone doesn't seem to be so different from talking to a passenger, and the latter did not appear to be correlated with crash rates. As evidence for the correlation accumulated, the idea of coincidence became harder and harder to accept. So researchers began to look for other explanations, and one seemed obvious on the surface. Most cell phone users were holding the cell phone in their hands, which seemed likely to mean less control over driving. This fact led many states and countries to pass laws requiring hands-free driver devices in cars. However, further studies showed that there was still a correlation between cell phone use and crashes, even when the devices were hands-free. So our explanation of this is, at this point, researchers began to question the assumption that talking on a cell phone is just like talking to a passenger. Brain scans conducted during simulated driving sessions soon showed that talking on a cell phone activates different areas of the brain than talking with someone sitting next to you. This offered a potential explanation for why talking on a cell phone might have different effects than talking to a passenger. Follow-up studies provided additional evidence for the idea that cell phone use is a source of distraction that can cause crashes with or without hands-free devices. Most shockingly, some studies have found that the distraction caused by talking on a cell phone while driving, even with a hands-free device, can make you as dangerous as a drunk driver. Texting or using other computing devices while driving is even worse because it causes the same type of distraction and also forces your eyes off the road. The National Safety Council now estimates that approximately 1.6 million car crashes each year, more than a quarter of the total, are caused by this type of distraction. So they offered a potential explanation for why talking on a cell phone might have different effects than talking to a passenger. When they went back, so the brain study confirms the fact that this stimulates something else in your brain, even if it's a hands-free device. So when they looked at the brain patterns, they found that talking on the phone, okay, is different than talking to a person in the car. So whatever that distraction is causing more of the accidents. So when we're looking at for confidence and causality, we want to evaluate whether it's a possible cause. We have discovered a correlation but cannot yet determine whether the correlation implies causality. In the legal system, possible cause, such as thinking that a particular suspect possibly caused a particular crime, is often the reason for starting an investigation. We have good reason to suspect that the correlation involves cause, perhaps because some of the guidelines for establishing causality are satisfied. In the legal system, probable cause is the general standard for getting a judge to grant a warrant for a search or wiretap. Cause beyond reasonable doubt, we have found a physical model that is so successful in explaining how one thing causes another that it seems unreasonable to doubt the causality. In the legal system, cause beyond a reasonable doubt is the usual standard for conviction. It generally demands that the prosecution show how and why, essentially, the physical model, the suspect committed the crime. Note that beyond reasonable doubt does not mean beyond all doubt.